So what's happening there is proton capture, and you're building up the light elements. And there's a huge amount written on this. And in fact, for instance, Weinberg's book, The First 3 Minutes, is a really, really nice introduction. And we don't have the time or space to go into the details of this. But the basic point that happens is light elements are synthesized. And by light elements, what I mean is deuterium, helium-3, helium-4, lithium. And then there is a bottleneck in the production of higher elements, and that's as far as the early universe goes. So, this leaves us with a kind of a massive problem that we have to solve. If we look around the room, now in fact what happens here, and of course we've got hydrogen, and the hydrogen is 75%, and all of this lot is 25%. Well, in fact, it's the helium, which is 25% basically. And it cuts off at lithium. So the question is, where does the carbon, nitrogen, oxygen, phosphorus in this room come from? And you surely know this, but I just want to get the full picture. The heavy elements are formed in stars, first generation stars, and then spread in space by supernova explosions, and then lead to second generation stars. So this was a discovery of the 1960s. Second generation stars can have planets. First generation stars can't have planets worth speaking of because there's no heavy elements to make the planets. And so this is one of the major discoveries. As the universe expands, you get nucleosynthesis taking place, light elements up to lithium, and that's as far as it goes. So you do not have the materials to make life by the time you come through at the end of nucleosynthesis. Nucleosynthesis comes to a stop because the temperature drops below the threshold for nuclear reactions. And after that, you've just got these elements left. And so what happens then, the crucially important feature is that the first generation stars form, and they cook the nuclear elements for a very long time, and they can create elements up to and including iron. They then blow apart, spread these through space, and this then coalesces to form second generation stars with planets.
Just before we get to the heavy elements, what happens to the antiparticle?
Oh.
In the picture, after pair production.
Okay, there's a whole thing which goes on here. The belief is that particles and antiparticles are very, very closely matched, and then there is a slightly out of equilibrium process which gives you a slight preponderance of particles to antiparticles. This has been the discussion through the decades. There was one group of people who suggest the universe is exactly particle-antiparticle symmetric, and what has happened is particles have coalesced out somewhere and antiparticles out there. So some of those galaxies up there are antiparticles, and you better not travel there because you'll be in deep trouble when you arrive there. It's more commonly thought now that instead, that isn't quite what happens, that there's a slight asymmetry in weak interactions which produces the asymmetry of particles to antiparticles, but it depends on an unknown particle called the X, which could, and it's one of these speculative things that we know the conditions it could happen, but we don't actually have a specific mechanism. And Professor Z will know a huge amount more about this than I do. Okay, now, the hugely important further thing that takes place is the following. As we go through, coming down, these things all go the other way. We build up, and the crucially important one is when ions and electrons form atoms. Because when you've got ions and electrons, the universe is opaque, and it's opaque because of Thomson scattering, because free electrons scatter very, very strongly with photons, and all of a sudden you get atoms. And this is at this temperature, this ionization temperature of about 4,000 degrees Kelvin. So all of a sudden, what were free electrons and proton nuclei become bound atoms, and all of a sudden, the universe becomes transparent, and it's a very, very dramatic transition that takes place. So this is at what is called decoupling. Why decoupling? Because at this time, the matter and radiation, which were in equilibrium, are now decoupled, and so the universe becomes transparent. And a model for this is what happens in the sun. As you cross from the interior of the sun to the exterior, the photon mean free path changes from at most a few centimeters to thousands and thousands of light years. In fact, here it changes, the photon mean free path changes from less than a centimeter to 1,000 million light years. The universe is unbelievably transparent today. That's one of the things what you should remember about it. We are seeing back to these incredible early times with basically no interference, but we are cut off by the surface of last scattering. So the surface of last scattering or surface of decoupling is the limit to which we can see. As we go back into the past, as the photons, it's transparent until we hit that time. It is this surface which emits photons which cool today to give us the 2.75 degree K microwave background radiation. So the microwave background radiation we can think of as being emitted by the surface of last scattering. These photons have then traveled freely towards us for thousands of millions of years, and we receive them today with these very sensitive detectors. But the point about it is that the universe was opaque before and becomes transparent at this time. Okay, now, what else is there? I'm not going to say much more about all of this at this time. I think that's as much as I'm going to say about all of these interactions. They are hugely complex. They're a great deal of fun to work out in detail. The nuclear synthesis details were worked out in about 1965 to 1970, were completed, as it were, and nothing much has changed since then. And so these are the processes to remember. The binding energies, everything gets broken up going back. They form going forward. Thermal equilibrium at these temperatures, and the temperatures follow the radiation. Pair production going up, pair annihilation going down. The forces will be unified at early enough times, but that's rather speculative, and I'm not going to go into that. And in these processes of building up, one of the most important is the nucleosynthesis, when we build up the light elements, but we can't build up the heavy elements because the universe is expanding too fast and the temperature is dropping too fast. And so the heavy elements must be created later on in stars, which are then spread through space by supernova explosions and allow second-generation stars to have use for planets. And then decoupling, there's the matter and radiation decouple, and the universe, which was completely opaque, suddenly becomes completely transparent. And that's a really important part of cosmology. And the radiation which was emitted at that time, we can think of the surface as emitting these photons. That's what we measure today as the background radiation, the 2.75 K radiation. Okay, how do we know all of this is true? Firstly, because we measure the cosmic background radiation at 3 degrees K, and second, we measure the element abundances. And I'm not going to go into the details of that, just to say that these agree with each other. It's most people's views. There are some problems. We don't know the interaction rates of the nuclear reactions as closely as we would like. One of the problems also is that the elements which are formed in the early universe then get messed around by stars. So what was the primeval abundance is not necessarily the abundance you measure in the light you get from stars at later times. So there's quite a lot of complication in this, but nevertheless the basic agreement is that these agree, and they agree provided the density of baryons is about 0.02 in the dimensionless units which we will be using. And this is really important, that this agreement comes only if the amount of baryons is approximately this amount, 0.02. I'll be talking about this quantity omega shortly, but just... Yeah, but we will need to remember that figure for later on. Okay. I want to get on to the relativity side of all of this. So, that's as much as I want to say about all of this lot, and I want to get on to the evolution of the universe itself. So, section 5, and you will be getting a copy of these notes, is the origin of the universe. Okay, so all of this, what we need to know is how does the scale factor behave? That's one of the things we need to know. Okay, now, to calculate this, you can calculate this in many ways. I'm just going to give you a brief note on the best way to do this. The best way to do this is to take the Ricci identity for the scale factor, for the... we've got our preferred velocity. And what you can do is take the Ricci identity. For general relativity people, every single vector in a space-time must satisfy this identity. Now what you do with that is you contract it with the 4 velocity again. So you contract it with a C, and then you set A is equal to B. If you do that, you end up with the single most important equation in cosmology, which is the Raychaudhuri equation. 3a double dot T over A of T plus kappa upon 2 into mu plus 3p, rho plus 3p minus lambda is equal to 0. And you get that from this equation by contracting with the u and then setting A as to B, which is contracting over A and B. And this equation will result, there are some more details in these notes which you will be getting out. Now this equation is what I'm going to call the Raychaudhuri equation, because an Indian gentleman named Raychaudhuri found that this applied in much more general circumstances, as I will say a word about probably in the last lecture. Now, why is this important? Because of the following. What you can do, you can plot A as a function of time, so A is a function of time. What does this equation tell you? It tells you A double dot. Now, what is A double dot? When you have a curve A of T, A double dot is the curvature. It is the rate of change of the slope. The slope is the Hubble parameter, and the rate of change of the slope is given by A double dot. And you immediately see from that A double dot is less than naught, is greater than naught. Now, hang on, I must get the signs correct here. A double dot is less than naught. A double dot is less than naught if mu plus 3p is positive and if lambda is less than or equal to naught. What that means is this curve is bending down going forward, but at the moment, at the present day T0, we know that the universe is expanding, so at the moment it's sloping upwards. If you have mu plus 3p positive, then that gives you a negative contribution to A double dot. Now lambda can give you either. If lambda is negative or 0, then that also bends down, and what that means is the following. We get the basic and most important singularity theorem. And the singularity theorem will be as follows. If lambda is 0, let's take that for simplicity, and mu plus 3p positive, then A of t goes to 0. A time t0 less than 1 over h0 ago, where the energy density will become infinite and the temperature will become infinite. And this is the basic singularity theorem. It's telling you the Einstein field equations. I should have emphasized that you use the Einstein field equations, which is where the lambda comes from and the rho plus 3p comes from. What it says is the following. The slope of the universe, a straight line will give you 0 a time 1 over h0 ago. If rho plus 3p is positive and lambda is 0, then this curve must bend down. So as you go backwards, you must run into the axis before this time 1 over h0. So the age of the universe is less than 1 over the Hubble constant. The Hubble constant being A dot over A evaluated today. So that's the slope of this line. This height here is the age of the universe, so is the present scale factor of the universe. And this curve runs into zero a finite time ago, where that time is less than the inverse Hubble parameter. Now,